Hello all, I'm Ghazi from Aalto University and I will be talking about foveated streaming of real-time graphics. Our work studies three methods of delivering foveated video streams of real-time graphics, including a novel post-processing based method which we call foveated warping. Let's start with an outline of the presentation. I will briefly introduce remote rendering and foveated rendering and foveated video encoding. Then I will discuss the three methods considered in this work, followed by a discussion on evaluation of the methods. Finally, I will conclude with a discussion of the results and future directions. Remote rendering is a relatively old paradigm of rendering computer graphics on a remote server and displaying the rendered graphics on a typically thin client. The rendering server executes all the application and rendering logic, then encodes the rendered frames and transmits them to the client. The client decodes and displays these frames. In interactive applications like remote desktop and cloud gaming, the client captures user input and forwards them to the server. Remote rendering has become an attractive proposition for graphics-intensive applications, particularly with the availability of cheap graphics cloud services and high-speed connectivity. It's the enabling application of cloud gaming and cloud XR. Remote rendering brings cloud flexibility and scalability to graphics computing. However, it is beset by challenging requirements of high downstream bandwidth and low latency. Human visual system has non-uniform visual acuity. This is due to the non-uniform photoreceptor density in the retina, as you can see here. The retinal region directly behind the lens, called fovea centralis or fovea in short, has the highest cone density and corresponds to the sharpest vision. The acuity of human vision drops steeply with eccentricity from the fovea. This also manifests in the highest partial frequencies visible to our eyes at a particular viewing distance. These are called cutoff frequencies at a particular viewing distance and a particular eccentricity. As you can see here, cutoff frequency is directly in front of the fovea and drops steeply with eccentricity from the fovea. Foveated rendering and foveated video encoding attempt to respectively render and encode images so that their quality profile matches the matches that of the human visual system. These techniques can potentially reduce resource usage and improve user experience. Further, these approaches can be applied and optimized in multiple ways, for example by considering scene geometry and lighting information, or in case of video saliency. We studied three methods of delivering foveated graphics in a remote rendering scenario. First is foveated rendering combined with normal video encoding, with frames having spatially uniform quality in the encoding phase. The foveated rendering was implemented with variable rate shading. Second, we consider foveated rendering with foveated video encoding. We implemented the foveated video encoding by varying quantization across the macro blocks in a frame. Lastly, we consider foveated warping, which is an human visual system based post-processing 2D image warp, which produces a foveated image. To implement foveated rendering, we used NVIDIA's variable rate shading API. Variable rate shading allows rendering different parts of a frame with different qualities by varying the underlying number of samples sampled to generate a fragment or a pixel. This can be used to implement foveated rendering, where the quality of the region in the scene on or near the viewer gaze is rendered with the highest sampling rate, and elsewhere the sampling rate is decreased. In our setup, we divide the frame into three zones: a high quality central zone with the highest sampling rate, a transitional region with a medium shading rate and a peripheral region with the lowest shading rate and hence the lowest quality. Foveated video encoding can be implemented in multiple ways. We use an approach where we vary the quantization parameter applied to a macro block according to the distance between the macro block and the gaze location. In practice, we add an offset to the QP calculated by the rate control algorithm of the encoder. The offset is calculated so that the quality profile roughly matches the quality profile of the foveated rendering setup mentioned in the previous slide and the foveated warping setup discussed in the next slide. In a gaze-centered frame, for a central circular region of diameter 0.25 times the width of the frame, the offset applied is 0. Beyond the circular region, as you can see here, the offset applied increases parabolically. We define foveated warping as a 2D image warping operation which takes as input a spatially uniform quality frame and produces an output frame where each pixel is mapped from n number of pixels from the input frame, n being inversely proportional to the cutoff frequency at the current pixel. In practice, we compress the rendered frame in post-processing. The compression is spatial in nature, so the operation is more like squeezing. The resulting frame dimensions in pixels are thus reduced. To get a pixel at a location XO, YO, we first transform the location into polar coordinates. Here, we then scale the R with the cutoff frequency at XO, YO, which then can be used to find the input pixel at XI, YI to be mapped to XO, YO. But since this R by FCNO is not easily invertible, we approximate it as a parabola, as A plus B into R square. As can be seen here, foveated warping changes the radial pixel density according to cutoff frequency from the gaze. We parameterize our foveated warping setup to be comparable to foveated video encoding, as discussed previously. Here you can see a normal frame and then the same frame warped with foveated warping, assuming the gaze is at the center, and then the same frame is unwarped here. We developed a prototype server capable of producing foveated streams of real-time graphics and a corresponding client. The client can display the video stream, receive and display the video stream, and also capture user input and optionally gaze information and forward these to the server. For evaluation, we configured the server to render a high-quality photorealistic Unity scene. The client and the server are also placed on the same network to prevent network artifacts from interfering. And then the underlying encoder, which in our case was the NVIDIA hardware encoder, was configured to use the low latency preset, and rate control was set as constant QP. Further, for testing, we also fixed the gaze at center, and each test comprised 60 seconds of predefined exploration of the scene. Now to the results. Here is the bitrate comparison of foveated rendered frames encoded with uniform spatial quality and normally rendered frames with uniform spatial quality at different QPs. The foveated rendered stream, FR stream, has equal or higher bitrate than normally rendered stream, NR stream. This is due to low interframe compression in FR, as verified by when we used only iframes for encoding. It is intuitive as well as in FR frames are visually more different from each other, as the high quality region around the gaze has different content in consecutive frames, and the low quality regions in frames may not be easily useful for prediction. Next, we compare the bit rates of foveated rendering, foveated video encoding, and foveated warping with respect to their corresponding foveated SSIMs. Uh, Foveated video encoding with quantization offset equal to 0 is equal to foveated rendering with normal encoding. Now looking at the plots, as expected, FSSIM is higher at lower QPs. But interestingly, for a particular frame size, foveated video encoding has slightly better FSSIM than foveated warping, especially when the foveated video encoding scheme is conservative with its offsets. We also conducted a limited absolute category rating hidden reference user study to verify the FSSIM results, as the DMOS scores are in the plot. They broadly follow the FSSIM results. This is a pilot study only, so the results are indicative of a DMOS FSSIM correlation. We do not attempt to quantify the correlation yet. Next, we consider latency. In the context of latency evaluation, a distinction between render resolution, that's the pixel resolution of the frame displayed at the client, and encode resolution, that's the resolution of the encoded frame, should be kept in mind. Looking at the line plot here, it's clear that with a given encoding resolution, foveated warping introduces a slight latency penalty. But given that for the same render resolution, foveated warping needs a lower encode resolution, comparing latency for a given render resolution is more appropriate. Now for a given render resolution, both the encoding and decoding latencies are lower for foveated warping, especially at higher render resolutions. Our work shows that foveated rendering alone for remote rendering does not reduce bitrate of the encoded stream. It may lower render resource usage at the server, but it does not reduce the bitrate and hence does not help the client necessarily. On the other hand, both foveated video encoding and foveated warping do significantly reduce bitrate of the encoded stream for a particular render resolution. Foveated video encoding has better quality per bit, as evidenced by higher FSSIM and DMOS scores, while foveated warping has lower latency for a particular render resolution, both in encoding and decoding, and thus would result in a lower end-to-end latency. Further, foveated warping can deliver a higher render resolution. Foveated warping can deliver a higher render resolution for lower encode resolution. This can be helpful, for example, in resource-constrained client devices, where the decoder has an upper limit on the maximum resolution of input encoded frames. This is the case in many mobile devices. Overall, these results indicate that foveated video encoding and foveated warping are suited for different use cases. If the requirements are low latency and high target resolution, foveated warping may be the more suitable solution. When lower compute loads and higher quality per bit is needed, foveated video encoding might be more suitable. For future work, we intend to conduct a broader user study with more participants and also with a VR component. We plan to include real-time tracking and varied content. Thank you.